Writing code that runs efficiently on a GPU is a black art, a skill that takes years to master. But what if you could automate it? What if you could get a large language model guided by the timeless principles of evolution to do it for you? In this video, I'm going to show you exactly that. This is the story of my workshop paper where I built an DIY AI researcher that learns to write its own GPU code. So, for the GPU Kernel Scientist, we're going to go over a bit of background. We'll cover more of this in follow-up videos, but they will cover the key ideas of GPU kernels and why they're important, and also some of the basics of evolutionary methods. And then I'll talk about the actual method and paper. So, for GPU kernels, the complexity of GPU processing is normally hidden from us by PyTorch, Keras, JAX, TensorFlow. These things essentially cover up a lot of the complexity behind the scenes, but sometimes the details really matter. For instance, DeepSeek, with their new R1 paper, they actually had a whole week of open sourcing their code to show exactly how they did this behind the scenes. Other things which people have shown have been important to make things faster: flash attention. People have been playing with nerfs, for instance, which require GPU kernels to make even practical. There's also Mamba, a new state space kind of model, which they have specialized GPU kernels to make work nicely. Often this is going to require writing CUDA code, which is NVIDIA's specialized code for writing GPU kernels, but there are equivalents for other GPU families, or you might need to do even lower level hardware. So the kind of speed ups available for this, even if you just look at a very simple matrix multiply of two matrices multiplied by each other, if you do a naive approach, just getting the GPU to one by one look at the different elements and add it all up, the kind of data rates you can get out of this are 309 gigaflops per second, which sounds like a lot, but actually it's way less than can be done if you write specialized kernels. For example, we can look at a blog post which describes how a GPU kernel can be written better and better in stages. So at the very beginning, with a naive version, they score only 300 gigaflops per second, but by the time they're through done all of their specialized operations, they can get to much higher rates. So a basic naive implementation will just multiply elements by each other like you would multiply it do a matrix multiplication in high school, and this will get you a certain speed. But as you start to go down into more and more specialized thing, looking at how GPUs can look at global memory, how they access it, how they pull it down into multiple cores who will operate simultaneously, you can suddenly start to get much better throughput by looking at how the GPU works in detail. And so I'm definitely going to skim through this for this video. Okay, suffice to say, there is some complicated stuff going on behind the scenes here, and there are GPU experts who love this stuff. So let's see why exactly I started tackling this problem. It was because there's an AMD Developer Challenge, which is a competition. It's like a Kaggle-like competition for writing AMD GPU kernels. Now for me, I'm not so concerned about whether it's CUDA or AMD or other devices, but it's particularly interesting because there literally isn't that much data on the internet about how to do it properly for AMD, and this makes it for a very interesting playing field, as it were, because LLMs clearly depend on the data that they have available. The question is, can we do this with actually very little data, very few examples, little in the way of data sheets, etc. So this very nice competition had 3 different kernels they were interested in doing, and so there's a floating point 8 matrix multiply thing, which is scaled in exactly the DeepSeek kind of way for doing these matrix multiplies. There's a fused MOE, mixture of experts kind of thing, and then there's an intention operation. I focused on the first one of these, but clearly these techniques could be applied to other things. That's the whole point of this, is it's going to be extensible. So here's the web page for the AMD Developer Challenge, introducing what they were going to do and the prize money. Always good that they incentivize people to have a look. Part of this was organized by the GPU mode website, which has leaderboards for all these things, and also a huge community of people who are super keen on GPU kernels. They also have a Discord channel where people can discuss the competition, and you also get to submit your answers manually via that if you want to. Though there is a command line interface which we're going to use because I want to be able to automate everything. So the big question is, can Gemini Pro 2.5 write AMD GPU kernels? And the short answer is yes, it can. The longer answer is kind of yes, but kind of how competitive is it going to be? And then the next question is, how can we actually get these optimized properly? So one of the key factors which is going to help us here is that the LLMs have got much better over the years. They can now fairly effectively write and make alterations to programs. They can compare methods, they can compare outcomes, and they can also create and combine instructions and then follow those instructions themselves. So this is all very good for writing and updating code, and many people have done this, for writing their own code bases. In addition, we're going to make use of the fact that these LLMs have kind of human notions of elegance and novelty, which is something which has been shown academically, but it's kind of surprising that part of the broadness of the training of these LLMs isn't just the nuts and bolts of typing in code, but appreciating whether code is nicely formed and well thought out. This elegance factor is often underestimated. Okay, so the approach to the competition, we're going to try and write high-performance FP8 AMD kernels. We're only going to use the LLM code capabilities. I don't want to have to understand this myself. It kind of defeats the purpose of this whole kind of experiment we're doing. The obstacles here is there's very limited AMD documentation. There are very few examples of AMD kernels, particularly for this low precision, and we can only run code via very limited REST APIs. I don't have access to one of these AMD server chips myself, but the competition has an interface whereby you can submit code, get compile time errors or whatever back. You can also get runtime errors and also an assessment of numerical goodness. And you can also run a benchmark. But the benchmark is not a profiler. The benchmark was just end to end. Did this code run quickly? And so you get a number in kind of microseconds about how fast these run. So what's the flow of execution going to be? We're going to get Gemini Pro to write these GPU kernels. It's going to be based on known working kernels, but these are going to be very far from what it's eventually going to write. So the initial kernels we are given in the competition is PyTorch kernels, which are written in a very unoptimized way. Basically, they calculated the 8-bit multiply by doing it in 16 bits and then converting it afterwards. So this, while it relied on the actually very efficient 16-bit multiplications, it's clearly we should be able to do better using 8-bit hardware in the AMD chips. I guess another thing to point out is that the fact that it's just I'm talking about AMD a lot. It isn't that this is the only alternative to NVIDIA, but it is clearly we're in a different kind of game than if we were just writing NVIDIA kernels, simply because there's so much NVIDIA information out there, and the LLMs are very familiar with that. What we're then going to use is the benchmarks that we've got from writing a kernel and use Gemini Flash to plan next iterations. So basically we're going to see how we did at the last set of kernel we wrote, and then plan out what we want to do next. And then we're going to get Gemini Flash to suggest experiments that it would like to do. So basically it knows the results. It can then decide, well, what experiments would be good to do from here, and then we can loop around to get the Gemini Pro to write some more like that code according to the design. So in terms of tricks that we're using here, I found that Gemini Pro is very effective, but you've got to have very relevant context. That's absolutely crucial. And so we could also imagine having a scheme where Gemini Pro itself could suggest context that it needs and behave even more agentically than it is in this kind of 3-step process so far. The other nice thing, there's evolutionary kind of methods, which I'll talk about in there'll be later videos which go into this a bit more, allows us to A/B test everything and just see what survives. And survival of the fittest kind of means that the best methods will percolate to the top. I've also found that Gemini Flash is actually pretty good at deciding what nodes to build on, like what are the right kernels to build upon, and it's also quite good at deciding what experiments it'd like to try. But what we also do is get it to estimate how these experiments might perform, like a range of how good the performance it thinks a kernel might be, and then guess how innovative it thinks that kernel or that step would be, that improvement. And so out of a whole bunch of different suggestions, we're going to pick the one which it thinks has the potential to be best, the one which it thinks has the potential to be least bad at improvement, because it has come up with a range, and we also want the one which it thinks will be most innovative. So out of the wide range of experiments I've got it to propose, I then force it to do the experiments which give it the highest, in its estimation, the highest potential outcome, the highest worst outcome, and also the most creative. So this kind of forces it to innovate, or at least maintain several different paths towards best. What I've seen from other papers is that they tend to just want the kernel which is the best and press towards that consistently. Looking at this from an evolutionary point of view and from an innovation point of view, it can actually help to have multiple different like a frontier which contains multiple different ways of doing things, and keep alive even things which are slightly worse if they're more innovative, because that innovation pool gives you more opportunities to find greatness later on. So here's a diagram of the operations which are being done by the different models. In the top left over here, we basically look at all the benchmarks accumulated so far and how all of these models relate to each other, like which is the parent of this kernel, like where did I come from. We then get it to suggest to itself what experiment do I want to do, which kernel is best to work off, and what other kernel will be good as kind of another reference, so it can kind of play off between the two differences. This allows a kind of a two-parent idea, which is another genetic thing, and in papers like AlphaEvolve is something that they also did, so I kind of like this idea. In the top right, we've got the experiment designer. Basically, I get it to, this is kind of a prompting strategy, I get it to create a variety of avenues which might be interesting for experiment, and then from those I get it to design multiple experiments, more than I need, but also these estimates of the potential performance improvements, and also the innovativeness, and then from that I just choose 3 experiments to do, which then causes the one in the bottom to actually write the kernels to follow the guidelines which it just proposed to create 3 new kernels which it can then test, which is over in the bottom left. In the loop we can fix up syntactic errors or numeric errors to some extent. I don't let it run forever trying to fix itself. We can also get to the benchmarks, which then feeds back into the big loop. And having the big loop is kind of the secret sauce to all of this, and how this evolutionary style method can work towards scientifically proving out good kernels. Okay, so let's look at that. You can see here that it's taken 2 different kernels, the 52 and the 46 kernel, and it's then decided why it wants to use those and explains it. I'd like to see the explanations just so I can see to what extent is it rationalizing its choices. And it seems to make a variety of different choices, so this is quite interesting that the Gemini Flash can do this. For the experimental design, basically it comes up with a description of the experiment it would like to do. It then comes up with instructions about how to do this programmatically, and here you can see the performance range that it thinks it has and the innovation score. So here I've just broadly described what an innovation score is and let it estimate it. So I'm then going to use that as a numerical fact to choose the different experiments next. For the coding part, I could show you the extensive GPU kernels this writes. Basically, this is very dense C++ kind of code written in HIP, which is AMD's CUDA equivalent. It's pretty good at writing this stuff. Even though there was little documentation, basically, once it ran into problems, we could, I would discover new articles. I would say to Gemini, would this article help maybe? And it would either say, that looks irrelevant, or, oh, it's kind of interesting. Okay, let's have it. And so basically, as the process continued, I would add a few extra bits to the context. But it's not as if I was actually understanding the problems it was running into or the code it was writing. This is a plus and a minus. Clearly, if I was one of the GPU mode enthusiasts, I could have given it even better prompting. But I wanted to have a nice, clean process whereby it would discover things for itself. Here is an estimate from asking Gemini Pro, like, what does this kernel actually do? Basically, it's decided to a whole bunch of interesting things. And I would be lying if I said I understood everything it was trying to do. It's a pretty sophisticated kernel writer. So in terms of end results, I'm reasonably happy with how this did. You can see here that the PyTorch base case took 850 microseconds. And this was using the optimized FP16 kernels, but not 8-bit kernels, right? But this is using the very best things which PyTorch currently uses. If you wrote the operation in naive HIP, so this is you naively wrote out the matrix multiply using the AMD HIP language, it's more like 5,000 microseconds. So this was, for me, this was kind of surprising how bad just writing this in like a proper kernel, but written wrong. Perhaps I shouldn't have been surprised given the earlier blog post, but okay, we got quite a big gap just by coding it ourselves instead of relying on PyTorch. Now, after the competition, which we only found out obviously after I did all this work, that the winning human entry was around 150 microseconds, so this is much, much quicker than the PyTorch can currently do. Once this stuff is open sourced, then PyTorch will incorporate this, hopefully. What the LLM could produce after this process, and I have to say we're kind of cut short, we got it to 450 microseconds. And this is where now, in retrospect, I can look back at the human solutions and see, well, what happened? How did we not get down to the very finest details? It seems like Gemini kind of overcomplicated things itself, which is interesting. There were some quite high performance, fairly short pieces of code, like maybe 150 lines or something. Gemini was producing more code than that, but it may be that also there was some detailed bit twiddling stuff, which Gemini had hardly ever seen any examples of that for CUDA kernels, because people often write loops out, or even if they have a DSL, which they will say is Triton or something, they haven't actually seen revealed exactly the bit stuff which is going on. GPU mode enthusiasts, on the other hand, did a fantastic job. So very impressive. And of course, now that job could be added to the context window of Gemini, and so suddenly we can look at where can we go from here. We're on a much firmer footing in terms of writing new stuff. So I participated in the competition with this, but also had the goal of writing this up as an academic paper, and was fortunate to have this accepted as a paper at the ESFOMO workshop. So this is a workshop at ICML 2025 for Efficient Systems for Foundation Models, the ESFOMO. They're interested in how to make foundation models as efficient as possible, from the very highest level down to the very lowest level, and this is kind of where this work lives. So I'm super proud that this was accepted at the workshop. I'll be super glad to meet people at the workshop if you're in Vancouver at the time. So there's a great deal of commentary on Twitter/X about the competition between AMD and NVIDIA and how this is now beginning to heat up. Certainly the AMD or server scale processors are really quite good, but they have a deficit in terms of catching up with GPU kernels. And this kind of work does suggest that this is possible to automate. I've actually put my hand up to try and do some of this. Here's something I found on Reddit, which is also very relevant to the GPU kernel question. Someone asked, so can someone use AI to finally improve ROCm, which is AMD's machine learning layer equivalent to CUDA or CUDNN? I know a group in Singapore. Since this was before the submission deadlines, I had to be a bit circumspect, which talks about this whole GPU kernel scientist. And this user, from what I can determine, is the AMD open source advocate, who kind of hangs out around these discussions and has suggested that he'll be able to hook essentially me up with a nice AMD card when they're available. We'll see whether AMD follows through. I'm keeping my fingers crossed. So to wrap up, LLMs can gain superpowers, particularly when employed in like a purposeful system. Building these systems is kind of a wide open question. There's a lot of different variations, a lot of different ideas people can have. Using these things agentically is super interesting. It's a whole different mode from which they were trained. And also, doing this work kind of proves that just do it is a motto which can pay off. The GPU kernel scientist was developed quite rapidly and is obviously gaining some recognition with the workshop and also from AMD, for instance. Other people have GPU kernel problems. Very interested to talk to anyone who's interested in this. I'll leave a link in the description below for the archive paper, which also has some additional materials where you can actually see some of these kernels. I'm looking forward to seeing some comments. Please get in contact if you're interested in this kind of thing, and in particular I want to continue this with a series of videos explaining like the forefront of AI kind of from a research perspective, but also in a yes, you can do it kind of perspective. Even though we can't be training a foundation model at home, even the GPU poor can do interesting research and essentially be at the forefront of some of these things, as long as we choose our targets carefully. Anyway, looking forward to seeing you next time. Cheers.